Well, in my talk today, I'm going to talk about the potential therapeutic uses of certain cannabis-derived cannabinoids and also certain synthetic cannabinoids as revealed by their pharmacological properties. And I'll be focusing particularly on research which I've been involved in. Before going on to that, I just want to declare that I have no conflict of interest. This presentation represents my own personal views of the information I'm presenting and doesn't represent anything, reviews from drug companies or indeed from my own university at Aberdeen. To begin at the beginning then, cannabis is a unique source of what we call phytocannabinoids, which are plant cannabinoids. And there's a great many of those, different kinds of those in the plant. They include THC-like compound tetrahydrocannabinol, that is type compounds, cannabidiol type, and cannabigerol type, but loads of other types as well. And altogether, there are at least 120 of these plant cannabinoids present in cannabis, plus at least 445 other compounds, including terpenes and terpenoids. The ones I'll be focusing on in my talk today are tetrahydrocannabinol type, cannabidiol type, and also cannabigerol itself. So before I get on to that, I just want to briefly mention approved therapeutic uses of cannabinoids. Some of them are already approved medicines. The first one of these to come along quite early on was THC itself, known as dronabinol or marinol, which was developed as an antiemetic and also as an appetite stimulant, and that became a medicine, an approved medicine in 1986. It's synthetic THC, however, it's not THC extracted from cannabis. One which came along slightly earlier than that medicine is a drug called nabilone or sesamet, which is a synthetic structurally similar to THC but different, and so it's not found in cannabis, but it is an approved medicine. And it's been approved as an antiemetic and was first licensed in 1982. So 3 or 4 years before dronabinol. More recently, another medicine to come along was Sativex, which is actually a cannabis extract, contains mainly delta-9 THC and cannabidiol. THC extracted from THC-rich cannabis and the cannabidiol from cannabidiol-rich cannabis. And it's been developed as an oral mucosal spray, so it can be sprayed into the mouth and absorbed from there, which is quite a good way to go because it avoids the liver. It was developed originally for use for multiple sclerosis and cancer pain, and approved originally in Canada, but subsequently became available in the UK as well, particularly for multiple sclerosis, pain and spasticity as well. So it's got THC and cannabidiol in it, but another medicine has come along much more recently, which contains mainly cannabidiol. And this is this compound here, this medicine here called Epidiolex, which was made available on prescription in the USA since November 2018 for severe childhood onset epilepsies, Lennox-Gastaut syndrome and Dravet syndrome. In parallel with that, other cannabidiol containing substances have been, or products have been developed, including the WeHemp company's cannabidiol oil drops. And these are are in fact legal but not approved medicines, unlike Epidiolex, which is both legal and an approved medicine. I think it's going to be, we're going to have to take a bit of more care with these other cannabidiol compounds that are products that are available in shops quite legally, but it'd be good if they were regulated more, maybe to make sure there weren't toxic compounds in there. For example, drugs which are used to help the plants grow, but like insecticides, which of course can be poisonous. So changes were recently made in the UK legal status of medicinal cannabis and of medicinal cannabinoids. The medicinal cannabis was moved by the UK government from Schedule 1 to Schedule 2. Schedule 1, the drug has little or no therapeutic potential in the view of the government, whereas Schedule 2, the drug has therapeutic potential, and specialist hospital doctors will be allowed to prescribe it. So now cannabis-based medicines are Schedule 2 and cannabis Schedule 2. Medicines derived from cannabis can now be prescribed in the UK by specialist hospital doctors for certain specific and exceptional clinical needs, with no other, if no other treatment works. The medicinal cannabinoids Sativex and Epidiolex were approved by NICE, that's the National Institute of Health and oh dear, I forgot what it's called. Never mind, NICE anyway, in the UK. Sativex for multiple sclerosis, spasticity and chronic pain, and Epidiolex have been approved, which means it's much easier for patients to get hold of those compounds as medicines. Importantly, the 2018 UK schedule change was prompted by anecdotal evidence. So anecdotal clinical evidence was emerged in the UK, strongly supporting the need for cannabidiol for epilepsy, childhood epilepsy. And this came, for example, from this lady who was the mother of a little boy, and she found that cannabis worked well to reduce the severity of his epilepsy. That helped to persuade the government to change its regulations about cannabinoids as medicines. And there have been many other anecdotal claims of this kind, other carers of children, for example. Sticking with anecdotal, it's interesting that quite a few years ago, this lady, Claire Hodges, not her real name, used to write articles in newspapers claiming that cannabis was good for her multiple sclerosis. She had to give up as a journalist because of that multiple sclerosis, but found that cannabis was very helpful for her. And that anecdotal evidence we gathered and published in this paper, The Perceived Effect of Smoked Cannabis on Patients with Multiple Sclerosis. And that we were able to do by contacting patients with the help of that lady I just mentioned, and also the Alliance for Cannabinoid Therapeutics. And what we found, or what we sent out when we set up the answers to our questions, really were that cannabis was good for improving the quality of sleep, reducing spasticity of multiple sclerosis, and reducing the pain of multiple sclerosis. And it was that which claim made by many people, which encouraged the search for clinical evidence to support that. And this search for clinical evidence was supported by a British Medical Association report in 1997, which I was involved with, and with a House of Lords Select Committee on Science and Technology report in 1997, which again I was involved with, and with the British government written response in 1999 saying they approved of the idea of carrying out clinical trials with cannabinoids. And there was also input from the Royal Pharmaceutical Society Working Party on cannabinoids, which again I was involved with. And finally, scientific evidence emerged supporting all of this. It's a bit unusual having the science at the end. And that science was published in this paper, Cannabinoids Control Spasticity and Tremor in a Multiple Sclerosis Model. That was research led by David Baker down in London. I was involved with it because of my cannabinoid expertise, but he was an expert on MS. So, approved therapeutic uses, moving on, pharmacological actions of plant cannabinoids. So THC, to begin with, it, among other things, targets cannabinoid receptors, which was discovered in the late 1980s and early 1990s, CB1 in the late 1980s, and first cloned in the USA in the early 1990s. And then subsequently CB2 receptors, which were discovered in the UK here in 1993. CB1 receptors are found mainly on neurons, that's nerves. CB2 receptors found mainly on immune cells. So THC can target CB1 and CB2 receptors as an agonist, so it can activate those receptors, but it's got loads of other uses as well, which I haven't got time to talk about today, but loads of other uses. And my main point I want to make here is that THC has a unique pharmacological fingerprint. So there are many other drugs which can target CB1 and CB2 receptors, but they don't necessarily share all those other actions of THC. So as I say, THC has what I call a unique pharmacological fingerprint. Important to bear in mind when considering new medicines. Moving on to other phytocannabinoids. Just a few of those shown here. Remember, there are over 120 in cannabis. Cannabinol, THCV, THCA, cannabidiol, cannabidiolic acid, CBDV, cannabigerol, cannabichromine. No time to go into their pharmacological actions now, you'll be relieved to hear. But they do have many actions and are not silent compounds, they are active compounds. And what I want to just mention is one point, which is that some of them have opposite effects. And so, for example, cannabinol activates CB1 receptors like THC, whereas cannabidiol can block those receptors in an allosteric manner. And THCV can behave as a competitive antagonist of CB1 receptor. So it has opposite effects. So they can fight each other, which is why maybe we should use a different way of writing down phytocannabinoids, spelling it. Instead of using phyto, P-H-Y-T-O, we should talk about phyto, F-I-G-H-T-O, because they fight each other. Another example is cannabidiol again, which can enhance activation of serotonin receptors, 5-HT1A, whereas cannabigerol blocks those receptors. So again, opposite effects. So just some potential therapeutic uses of plant cannabinoids. Just some phytocannabinoids other than THC I'm going to be talking about. Start with cannabidiol. One potential use it has is to treat chemotherapy-induced nausea and vomiting, and several other disorders as well, by enhancing the activation of 5-HT1A receptors. And then cannabidiolic acid, amelioration of chemotherapy and chemotherapy-induced nausea and vomiting through enhancement of 5-HT1A receptor activation. And we published work data on that a while ago for cannabidiol and also for cannabidiolic acid. And in both cases, the effects we saw seem to be 5-HT1A receptor mediated. CBDA was found to be more potent than CBD, which is interesting. So here we see the structures of CBDA, cannabidiolic acid, and of CBD, cannabidiol. And they're both present in cannabis. And what happens is that cannabidiolic acid breaks down to cannabidiol. So it's the precursor of cannabidiol, particularly when you heat the cannabis, it breaks down in that way. Another compound, which is a synthetic compound, because I'm moving on to those, is this compound HU580, which is structurally very similar to cannabidiolic acid. Instead of the carboxyl group, it's got a methylated carboxyl group shown there on the left. And interestingly, HU580 is much more stable than cannabidiolic acid, which because it lacks stability, it's rather unstable, it lacks therapeutic potential really. It's not druggable because it breaks down too quickly. But the one on the left prompted the development of that compound on the left, which was designed and synthesized in Rafik Meshulam's laboratory in Israel. So to step back a bit, the aim of our research then with the HU580 was to establish whether it does share the apparent ability of CBDA to enhance 5-HT1A receptor activation, both in vitro and in vivo. In vitro experiments we performed, which are the ones shown here, which we performed with Chinese hamster ovary cells expressing 5-HT1A, human 5-HT1A receptors. And then in vivo experiments were carried out with a 5-HT1A antagonist using rat models of nausea and anxiety, and that was carried out by collaborators in Canada. And these compounds were synthetic cannabidiolic acid and synthetic HU580. And what we found was that HU580 enhanced the in vitro activation of 5-HT1A receptors even more potently than cannabidiolic acid. It also displayed greater potency than CBDA at reducing signs of both acute nausea and anticipatory nausea in rats. And it also shown previously for CBDA, these effects of HU580 on signs of nausea appeared to be 5-HT1A receptor mediated, as shown by study experiments done with an antagonist. And HU580 also displayed greater potency in the CBDA at producing signs of stress-induced anxiety the animal model shown there, the rat model, and it increased the length of time they chose to spend in a light box after entering a dark box, which is a sign of reduced anxiety. And these anxiolytic effects of HU580 and CBDA also appear to be mediated by 5-HT1A receptors. So HU580 is likely to be more druggable than CBD acid because, as I mentioned earlier, it's got greater stability than CBD acid. It also displays greater potency than CBD acid in those assays, as I just mentioned. And interestingly, it has a broader bell-shaped dose response curve. I didn't mention that before, but CBD, CBDA, and HU580 all have bell-shaped dose response curves, which means they work over a range of doses, not at very low doses, but nor at very high doses, but only at in a range of intermediate doses. And that range is broader for HU580 with the other compounds, which is encouraging. And that work was published in British Journal of Pharmacology in 2018, and it was a joint effort between Canada, Israel, and here in Scotland. So possible future directions, where next? We need to seek out all the unknown pharmacological actions of HU580 and CBD acid. We need to perform clinical trials to establish whether what the results we've obtained are clinically relevant. Are our data which we obtained preclinically hopeful or hypeful? And we need to identify and explore all other possible therapeutic uses for HU580 and CBDA that might result, for example, from enhancing 5-HT1A receptor activation. And there are a number of possibilities shown here in that box at the bottom, but unfortunately no time to talk about that now. Interestingly, as far as clinical studies are concerned, it's interesting that some evidence that cannabidiol does work in humans, and that was work obtained in Brazil by Zuardi et al. And they worked with, compared cannabidiol with this compound, ipsaperone, which is a direct 5-HT1A receptor agonist. And they found that CBD at 300 milligrams per kilo orally decreased anxiety induced in healthy humans by simulated public speaking, of all things. But that produces signs of anxiety, and that anxiety was reduced with CBD at that dose. And that was supplied by Raphael Mishulam again, that CBD as it happens. And then 5-HT1A receptor agonist ipsaperone also decreased anxiety. So it might an excellent benefit to risk ratio be obtained for the release of anxiety by co-administering a 5-HT1A receptor agonist with HU580 or CBDA or CBD. Probably best would be HU580. That's something that would be interesting to explore. It's also worth pointing out that the group in Brazil found that CBD worked at 300 milligrams per kilo against anxiety, but it didn't work at 150 milligrams per kilo, and nor did it work at 600 milligrams per kilo. So it worked at only at the 300 intermediate dose, showing that it has a bell-shaped dose response curve similar to what we found, suggesting that it may indeed be acting through the 5-HT1A receptors in the same way that we found in our experiments. Potential therapeutic applications of cannabidiol, some involve 5-HT1A receptors, as shown there, shown there on the right, and possibly also its anti-schizophrenia effect may be involved 5-HT1A receptors. That remains to be explored. And the same for its ability maybe to be effective against some neurodegenerative disorders, as shown there at the bottom. And of course, those are all potential therapeutic uses of CBD, but one actual use is for epilepsy, as I've already mentioned. But I have no time to talk more about the potential applications, therapeutic applications of cannabidiol. It's worth bearing in mind, though, that cannabidiol does have unwanted effects as well as wanted effects. This it was nicely described by Hustis et al. In this review article. And they found that it's not risk-free. For example, in clinical trials with epileptic patients, it's been shown that cannabidiol can produce signs of somnolence, drowsiness, lethargy, sedation, and fatigue. But of course, it's not unusual for a medicine to have adverse effects. And it's not the adverse effects which are a problem, it's the benefit to risk ratio that's important. And of course, it may be interesting to exploit the effect to treat insomnia, this effect to treat insomnia. So an adverse effect may actually be beneficial for other groups of patients. Moving on to cannabigerol, it's possible that it might be good for relieving pain because it can target alpha-2 adrenal receptors as an agonist. That's something we discovered a year or two ago, and we published in that paper shown there. And there's the structure of cannabigerol at the bottom. And as I say, we obtained evidence that it's an alpha-2 adrenal receptor agonist. And that was obtained in experiments with mice using a carrageenan model of allodynia, mechanical allodynia, and a mouse model of persistent inflammatory pain. We found that cannabigerol blocked both those signs of pain, and it behaved like clonidine, which is an established alpha-2 agonist, which is used to treat such disorders. And its effects in these animal experiments was blocked. These effects were blocked by an alpha-2 adrenal receptor antagonist, yohimbine, which also blocked, of course, clonidine. So cannabigerol may be good for pain relief. That's something that has yet to be explored in clinical studies. Moving on to another one, THCV. That's really one of my favorite plant cannabinoids, because it's one which the group I was working with in Oxford many years ago, back in the 1970s, we co-discovered in cannabis. There on the right, we see the structure of THCV, which has got a 3-carbon side chain, as shown there. And then on the left, we have delta-9 THC, which has got a 5-carbon side chain. That's the only difference between these two molecules, both of which, of course, as I said, are present in cannabis. So delta-9 THCV is a phytocannabinoid, and in our initial experiments with it, we found that it actually can behave a bit like THC in vivo. That was in work done in mice. It actually produces signs of catalepsy at highish doses. However, subsequently, we found that it can also behave as a CB1 neutral antagonist in vitro and also in vivo. And we think that's its main effect, not being an agonist, but being an antagonist. And it also behaves as so it can block CB1 receptors, but it also behaves as a CB2 receptor agonist in vitro and also in vivo. So THCV then, because it can have that combined effects of blocking CB1 and activating CB2, might be good for treating, ameliorating diabetes-related kidney damage. And that's ongoing research. We haven't got enough results yet for me to talk about that. But THCV may also be active against nicotine dependence, possibly by activating CB2 receptors and maybe blocking CB1 receptors to produce that beneficial effect of reducing nicotine dependence. The work we did with the nicotine dependence was actually with delta 8 THCV rather than delta 9 THCV. So we used delta 8, which has got that which has got the double bond on the left-hand side there, rather than the right-hand side of a top left-hand ring. But its pharmacology of these two compounds is very similar. We initially presented data on this at a meeting of the British Pharmacological Society back in 2007, where we found that we showed that indeed delta 8 THCV can behave as a CB1 antagonist and as a CB2 agonist, just like delta 9 THCV. And we went on then to show, this was in collaboration with a group in USA, that delta 8 THCV is good for reducing signs of nicotine dependence, reduced signs of nicotine dependence in animals, as shown there at the bottom. Delta 8 THCV did not inhibit intravenous administration of self-administration of cocaine, so it didn't stop effects of signs of cocaine dependence, but did reduce signs of nicotine dependence. And we subsequently published that in a full paper in the British Journal of Pharmacology in 2019. So just some potential therapeutic uses of plant cannabinoids, but moving on, some potential therapeutic uses of synthetic cannabinoids. I've already mentioned HU580, but there are many other possibilities. One of these actually is a water-soluble prodrug of THC, for a prodrug with a THC-like structure, for example, for treating glaucoma. And that was work done down in Mississippi in the USA in research led by Mahmoud El Soli. And they worked with this compound, which they developed, which is an analog of THC. Its structure is similar to THC. That's the structure of THC, but it's got this, this delta 9 THC, but it's got this huge group added onto it, which makes it water soluble, but also inactive. So it's what's called a prodrug because it can break down to THC. So it's a water soluble THC prodrug, and they applied it directly to the eyes of rabbits in which glaucoma had been induced. And they found that this drug, this prodrug, diffused to various parts of the eye when it was injected, when it was applied to the eye, and then decomposed to THC, which then lowered intraocular pressure in these rabbits. And this lowering effect of this prodrug was greater and 1 hour longer in duration than the IOP lowering effect of THC. So it looked like it was a better medicine for glaucoma than THC. But that was just in rabbits. It remains to be seen what happens in humans. Interestingly, a year or two before then, a few years before then, my group, together with collaborators from the USA, had come up with another prodrug, another water-soluble form of THC. There on the left we see THC, and there on the right we see the drug we developed, O1057. It's delta 8 THCV in this case rather than delta 9. And that group was added to the molecules, rather similar to the group added by the El Soli group in their experiments. And that made the compound water soluble, but it still produced THC-like effects in animals. We never explored the possibility that, though, that it might be a prodrug. That's something it might be worth going back to. So say with delta 8 THC in this case. Another example of drugs that can target the endocannabinoid system, for example, to relieve pain. So the other side of the coin now, I'm talking a bit about the endocannabinoid system. discovery of this began with the discovery that there are CB1 and CB2 receptors, which were cloned in 1990 and 1993, as I've already mentioned. And the discovery that this prompted the search for what we call endocannabinoids now, drugs which are produced in our own bodies that can interact with these receptors, because it was generally agreed that it was unlikely that we'd produce these receptors in order to get high in cannabis. There must be some other reason for them. They must have physiological function. And that led to this search, and the search resulted in the discovery of anandamide, the compound shown there on the left, in research led by Rafi Meshulam. I was lucky enough to be involved in that research, and we published our first paper on anandamide in Science in 1992. And then a year or two later, another one came along, again in research led by Rafi Meshulam from Israel, and this was 2-arachidonyl glycerol, or 2-AG, which again behaves as an endogenous cannabinoid, which means it's produced in our own bodies, and when it's released, it can act on cannabinoid receptors. And there are many other compounds which have now been identified as being endocannabinoids, but no time to talk about that now. But you can read more about that in that article, for example, if you want. As far as the anandamide story is concerned, we carried out our experiments with the mouse isolative acetopherins, which is in an organ bath, as shown here in this slide. And what we do is to stimulate it electrically, and that produces contractions. If we add THC, it reduces the size of those contractions. So the contractions are of smooth muscle of the acetopherins, and what happens is when we stimulate the tissue, we actually stimulating nerves, which then release contractile transmitters onto the smooth muscle to produce contractions. And these release transmitters are ATP and noradrenaline. And THC, as I mentioned already, reduces the size of those contractions, and it does so by reducing the release of ATP and noradrenaline onto their contractile receptors. And we found that anandamide behaves in the same way, and we get this nice dose response curve here for anandamide's ability to reduce the contractions produced in this assay. And we published that, as I mentioned already, in Science. So endocannabinoid system, importantly, is autoprotective in a number of disorders. That means that, by that I mean that endocannabinoids are released onto their receptors in a way which can be beneficial for health. And here are a number of examples. No time to go into any details now, but there are a lot of potential uses for drugs which can augment the protective effect of endocannabinoids. Just mention one example, and that is pain. Before I go on to those drugs, I'd just like to mention this publication, which came out quite recently, 2019. And this was this paper included a description of this lady here, Mrs. Jo Cameron, who lives quite close to where I live here in Aberdeen. She lives up in Inverness, a few miles north of here. And she's hardly able to feel any pain at all. And she says she feels very happy-go-lucky. And interestingly, she actually has higher normal levels of anandamide circulating in her blood than most people. And that is due to her greatly reduced ability to metabolize anandamide. So it builds up more in her body. And that reduced metabolism is because of genetic abnormality in her anandamide metabolizing enzyme, fatty acid amide hydrolase. Worth bearing in mind, though, that pain does have that conditions that this condition is a source of risks as well as of benefits, because pain can be protective. And sometimes she says when she's in the kitchen, she can smell burning meat, and that's actually her burning because she's put her hand on the stove, but she doesn't feel the pain. So pain is not altogether a bad thing. So drugs that elevate tissue levels of released endocannabinoids by inhibiting their metabolism or cellular uptake have therapeutic potential. And that lady what happened to her fits in with that as a possibility. And another possibility is that drugs which are selective positive allosteric modulators that strengthen the activation of CB1 receptors by release endocannabinoids also have therapeutic potential. So instead of developing a drug which increases the levels of anandamide, it would be interesting to develop a drug which strengthens the activation of endocannabinoids by endocannabinoids of cannabinoid receptors. And that second possibility really was prompted by, was prompted by our discovery here in my lab that allosteric modulation of the CB1 receptor is possible. In other words, that the CB1 receptor has an allosteric site. Here then we see a diagram showing the orthosteric site of the CB1 receptor, which is shown there at the top by that little box. And the drugs like THC can activate those receptors to cause the release of transmitters, release of various messengers. But the CB1 receptor we discovered also has an allosteric site as well. That's shown there. And the idea is that that in fact it's been shown that activating that site with a positive allosteric modulator can strengthen the binding of orthosteric agonists to the receptor, and also strengthen the signaling resulting from the activation of the receptor. So there are therapeutic possibilities for this that could be exploited, and that's something which we've been exploring. And this was work done in collaboration with a group in Boston, USA, a group led by Ganesh Thakur, who's a medicinal chemist, and he came up with a number of compounds, including this one, GAT211. And we found that, for example, that GAT211 behaved as a CB1 receptor positive allosteric modulator, as indicated by its ability to enhance the activation by anandamide. It enhanced the agonistic effect of anandamide in the vas deferens by its ability to bind to by slowing the rate at which it dissociates from binding sites on the CB1 receptor, and by enhancing the binding of a ligand to the CB1 receptor, the ligand being tritiated CP55-940, CP55-940 being a CB1 agonist which targets the orthosteric site. Here we see the results we obtained with the vas deferens, and you can see that the effect of anandamide was greatly enhanced by GAT211. Here we see the dissociation binding studies, in which we found that GAT211 slows the rate of dissociation of tritiated CP55-940 from CB1 receptors, in this case, receptors on mouse brain membranes. And here we see how GAT211 also enhances the binding of CP55-940 to CB1 receptors, this time human CB1 receptors in Chinese hamster ovary cell membranes. Sorry, Chinese hamster ovary cell membranes. So, selective positive allosteric modulation that strengthens cannabinoid CB1 receptors by released endocannabinoids have therapeutic potential, and we published that in the evidence for that in this paper. So CB1 positive allosteric modulator, GAT229, another one, can reduce intraocular pressure in mice with which have genetic ocular hypertension. So moving on then from pain, and there's also evidence that by enhancing activation of CB1 receptors, you can treat glaucoma. Interestingly, there's now also evidence that the CB2 receptor has allosteric sites. And that CBD can target both CB1 and CB2 allosteric sites. The first work for that, the first evidence for that really came from our lab, my lab, back in 2007. In that the results we obtained suggested that CBD showed that it was displaying unexpectedly high potency as an antagonist of CB1 and CB2 receptors, suggesting it wasn't acting in the usual way as a competitive antagonist. Further research with CBD and the CB1 receptor was obtained in Canada, and they went on to show for sure that CBD is a negative allosteric modulator of the CB1 receptor. And then more recently, research also results from research was also obtained showing that CBD is a negative allosteric modulator of the CB2 allosteric site. I've just mentioned CB2 allosteric site. The first evidence for that was obtained in Switzerland with this compound, pepcan-2, which is a naturally occurring compound, which was behaved as a CB2 positive allosteric modulator, but as a CB1 negative allosteric modulator. And then more recently, other drugs which can behave as CB2 positive allosteric modulators have come along, and that's research carried out in my lab and also very importantly in Italy by medicinal chemists who come up with some very interesting compounds, one of which is shown here, and which has a nice CB2 allosteric modulatory effect and is a positive allosteric modulator of CB2 receptor. We've gone on to explore that a bit further to consider possible therapeutic use for such a molecule. CB2 receptors are highly expressed by chronic lymphocyte leukemia cells, and we found that activating those cells with the CB2 in those cells with 8WH133, which is a direct CB2 agonist, significantly decreased the viability of these blood cancer cells. And the CB2 positive allosteric modulator, EC21A, which is one of the compounds developed by the Italian group I mentioned just now, significantly enhanced this anti-viability effect of JWH133. So it's possible that a CB2 PAM might be effective against cancer, either when co-administered with a CB2 agonist, and those agonists might include THC or indeed THCV, or some other agonist like JWH compound, or it might be possible that even by itself, the CB2 PAM might be effective against cancer by enhancing the effects of endogenously released endocannabinoids. That remains to be seen. So I've talked a bit about synthetic cannabinoids, HU580, a water-soluble prodrug, and drugs that target allosteric sites. It needs to bear in mind, though, that some may be toxic. Some synthetic compounds may be toxic. One example is rimonabant. That was the first CB1 receptor antagonist to be developed. It's developed by a drug company, Sanofi, and they were interested in it because as a potential treatment of obesity. They carried out clinical trials, it worked well, so that it was approved in Europe as a medicine for obesity. But unfortunately, although this wasn't picked up in the clinical trials, some of the patients became suicidal when they took it, or even killed themselves. So rimonabant had to be rapidly withdrawn. So it had toxic as well as beneficial effects, possibly because it's, we don't know for sure, possibly because it's an inverse agonist, which means it can switch off background signaling of CB1 receptors. Designer drugs are also problems. These are drugs which activate CB1 receptors. They're synthetic compounds not found in cannabis. They activate CB1 receptors very much more strongly than THC or anandamide, and they produce dangerous effects as a result, including severe kidney damage, and they again can kill people. These drugs were drugs which were discovered and developed by friends of mine, some of them, all medicinal chemists who were good scientists and were developing these compounds for scientific use as scientific tools, pharmacological tools. But of course they published their results, and so other people could see how to make these compounds. They did that, sold them online as legal highs, and the rest is history. Now, of course, they are illegal. And there's lots of other toxicity stories I haven't got time to go into. As far as the preclinical work is concerned, one challenge now is to establish whether what has been shown to indicate possible promising therapeutic uses for cannabinoids is at hype or hope. So more clinical trials are needed. It's going to be very important, I think, to do that. The rapidly expanding unregulated cannabinoid market is something that also needs to be looked at again, I think, when these drugs appear in shops when they haven't been properly regulated. We need to make sure that those products are safe before they're given to people, people are allowed to buy them. But that's really another story. I should also mention, it's not listed here, that I think a very important source of information for the medical uses of some cannabinoids, particularly derived from cannabis, are people who self-medicate or carers of people who are given cannabis to help with their disorders when other drugs don't work. I'll just move on. If there are any questions or comments, there'll be a question and answer session shortly when we can deal with those. Before doing that, though, I just want to mention sources of information about the pharmacology and therapeutic potential of cannabis and cannabinoids. And of course, they can be found in articles and journals published, which have been authored by me and by many other people as well. And there are certain books, including 2 books which have been edited by me, which I'll mention in a moment. There are also important societies that are both relevant and eminent. And one of these is the IACM, the International Association for Cannabinoid Medicines, which focuses particularly on clinical aspects of cannabinoids. So it's of particular importance to physicians, patients, but also to scientists and drug companies, all of whom and the members of society are made up of physicians, patients, scientists, and drug company members as well. And then the International Cannabinoid Research Society, which has been around slightly longer than the IACM, but is more scientific. It meets annually. It met annually in New York, in North America since 1992, but also in other countries since 1998 as well, meeting every other year in the USA. And it focuses mainly on cannabinoid science. As I say, I co-founded that. As far as the 2 books I mentioned are concerned, one of these is the Handbook of Cannabis, which contains chapters by a lot of different authors, clinicians, and scientists, and they're really great authors, and they're great chapters. And the other one is more on the endocannabinoid system, if you're interested in that, which I edited. And again, a number of different authors, great authors, contributed to that book. And with that, I'll come to the end of my talk. Thank you very much for listening.
Well, hello, it's my pleasure to ask Roger some questions on his talk. My name is Franjo Grotenhamen, and I'm the Executive Director of the International Association for Cannabinoid Medicines. And I know Roger for about 25 years or so. And well, I was very impressed by your talk, Roger. It was excellent. And I think some of the people might want to get more information on the different ways cannabinoid receptors can be acted on. There's agonism, antagonism, positive allosteric modulation, negative allosteric modulation. And there are even some molecules, for example, THCV, which maybe have sometimes as agonists and antagonists. Perhaps we can start with the last one. You first found out in your lab that it was an agonist, and then later it was an antagonist. perhaps you can elaborate on this a little bit.
Yeah, okay. So our first experiments with THCV were carried out many years before the discovery of cannabinoid receptors. What we found was that when we used an in vivo assay for THCV, which was the one we also used for THC, THCV behaved like THC. And of course, that would suggest maybe that it's, when the receptors were discovered, maybe it's acting on CB1 receptors as an agonist. But of course, we've no idea whether what the actual mechanism was that underlay its effect in vivo in those very early experiments. It could, for example, be that the THCV was metabolized to something else. We just don't know. And subsequently, we were able to show when receptors were discovered that it can target the receptors, but behaves as an antagonist of those receptors. So maybe THCV was acting through a different mechanism to produce the effects we first saw, which was, as I say, signs of catalepsy in mice.
So this was not a question of dose or something?
It could also have been that, but we had to, maybe if you give very high doses, you start getting agonist effects. There are drugs which are called partial agonists, which have low efficacy, and you need to give quite high doses to get an effect. Okay. And then the effect may not be very strong anyway.
Okay, so at a lower dose, you will expect antagonistic effects. Yeah.
Yes, but it could be that the THCV wasn't acting on CB1 receptors to produce the agonist effect. All we knew was that it produced a similar behavioral response to THC, but we don't know if the mechanism was the same.
Okay. And you in your talk, you talked about the antagonistic effect of CB2 receptors, which you detected in your lab. And later it was found that it was not an antagonistic effect at the orthosteric site, but a negative allosteric modulation. And I think this is something that people might not well understand. What is the interaction between THC and CBD when it comes to agonistic effect of THC and negative allosteric modulation? Could you a little bit elaborate on this?
Yes, okay. So THC, as I mentioned in my talk, THC, like other agonists, will act on what's called the orthosteric site on the receptor. That's to produce signs of activation of the receptor. But some receptors, a lot of receptors actually also contain what's called, express what's also called an allosteric site, which is quite different. It's, when you target it, you don't normally get an effect. Only what you do get is a strengthening or weakening of the effect of activating the orthosteric site. And CBD seems to be an allosteric modulator at CB1 and at CB2 as it happens. And so what it does is and it's a negative allosteric modulator, so it weakens the activation of the receptor by the direct agonist.
And this is the reason why CBD is antagonizing some THC effects. So for example, psychedelic effects or tachycardia. This is the modulation, the negative allosteric modulation, I think.
That would fit in, although there may be other actions of CBD which are involved in that as well. We don't know.
Oh, yeah, okay. And sometimes with the synergistic effects of THC and CBD, and this is also because there are other effector systems are involved. Is it right? Or?
Yes. Well, for example, CBD has anti-inflammatory properties, and I think THC also can be good for treating inflammatory disorders. So they would be maybe acting together in a synergistic way.
Yeah.
I guess. It's just a guess.
So this is, for some indications, it may be good to give THC and CBD together, for example, inflammatory pain, for example?
Well, absolutely. And of course, there's already one approved medicine where the two are given together for the treatment of multiple sclerosis in the form of Sativex.
And there may be other indications where it may be not very good, for example, appetite loss, because CBD is not increasing appetite, but more blocking appetite, and THC is increasing appetite.
Yeah, yeah.
So you have to look from indication to indication to look.
Oh, absolutely, yes. And of course, CBD may be reducing appetite by blocking or reducing the effects of endocannabinoids, because they're released in a way which increases appetite.
Okay, very good. And this may happen also with other cannabinoids, which we are only starting to understand, I think.
Yes, yes. There's an awful long way to go still. Cannabis is an amazing, like a treasure chest, really, of chemicals which are of potential interest, and people haven't really studied all of them yet. There's a long way to go.
So we have more than 50 years of research, and the coming 50 years will be as inspiring as the last 50 years, I think.
I think so, yes. And of course, we know a lot more now about the endocannabinoid system as well, and about cannabinoid receptors, and about how some of the phytocannabinoids work. But for those phytos where we know something, we don't necessarily know everything. And there may be further actions that remain to be discovered even for drugs like cannabidiol.
And what is your lab doing currently, or what is the most fascinating fields now for you? Maybe phytocannabinoids or endocannabinoid system. What do you feel is the most interesting issues you would like to work on, or you would like to see others work on in the next 10 years, for example?
Well, we're working particularly on allosteric site at the CB2 receptor at the moment. I've often collaborated with medicinal chemists. I find that amazingly useful way of proceeding as a pharmacologist. So I do the pharmacology and they make the compounds, and it's an interesting collaboration always. So I'm collaborating particularly with a group in Italy who is developing CB2 allosteric modulators, and we're studying how they work and how they might be used therapeutically, for example, to treat cancer, but that's at a very early stage. I'm also interested in maybe looking again at THEV and seeing whether it would be good for treating some of the problems of diabetes, particularly damage to the kidney, which is something which remains to be investigated. But I have collaborators in Aberdeen who are experts on that.
Okay. And what do you think is the difference between rimonabant and THCV when it comes to side effects? We know that rimonabant was taken from the market because I think it is a full agonist at the CB1 receptor, antagonist at the CB1 receptor, and THC maybe not have these strong side effects. Is it right? Or?
Someone may know why rimonabant produced suicidality. I don't know, but what I do know is that that compound, rimonabant, it blocks the CB1 receptor, okay, but it's also what's called an inverse agonist, which means even when there's no other drug around to block, it affects cannabinoid signaling in the body by reducing the background signaling of CB1 receptors. So CB1 receptors, even when they're not being activated, are active to some extent. So there's some signaling going on, and it switches that off. It's what's called an inverse agonist. Whereas THCV seems to be what's called a neutral antagonist. So it blocks the effects of activation of drugs which activate the receptor directly. But it by itself, in the absence of the agonist, it doesn't switch off that background signaling. So it's neutral. And that may be a good thing. But we don't know for sure where the suicidality came from with rimonabant. At least I don't know for sure.
Okay. And you mentioned that much clinical research has to be done in the future because we have a large potential, therapeutic potential of CBD and THC, and we do not really know which indications, which diseases can be treated successfully. But at the same time, I always wonder, what should we do with, for example, a patient who experiences, well, THC helps me with restless leg syndrome. What should we deal with this patient? Should he get an exemption, or how should we deal with it? Should he be treated as a criminal, or there will be a transition period, I think, because we have decades of research to be done, clinical research, to get everything out of it. And what should we do in the future with such patients where I'm not sure? Yeah.
Yeah, I think that's a very important question. I think that people who self-medicate and think it's being successful, and other drugs that they have access to, approved medicines don't work, but the cannabis for some reason or other, or cannabinoid for some reason or other, does work. I think that's a very important starting point, and we need to explore that much more by interacting much more with patients and also with carers of patients as well. And then we need to follow it up with proper clinical studies to see whether what they're claiming is true, to optimize the medicine that they're taking by coming up with a medicine which produces maybe fewer adverse effects, if there are any adverse effects, but maintains the beneficial effect. And so we need to, as we did for multiple sclerosis patients, we need to talk with those patients and then move forward and do clinical trials, and also look at the science behind it all, as that might help to improve the therapeutic development of such medicines.
Roger, I would like to thank you for this great talk and for answering my questions. And I hope the audience will appreciate what you have done in the recent years. It was impressive what you did in the last 45 of even more years under research.
Yeah, more.
Yeah,
yeah, and I'd like to thank you for leading such a great society, the IACM. It's amazing.
So, bye-bye, Roger.
Bye.